S means Michigan State.
And Schwarzians.
And Schwarzians.
Thank you, thank you. So thank you for the opportunity to be here and to give a talk on this nice conference. A really nice one. There were so many so advanced talks in the last days. So definitely we need some break. Everything I will tell will be accessible to high school students or at most undergraduate students. And I will start, so I will explain actually everything on the way, but first of all, I recall what is now some interesting topics is related to something that is not in the title, and something that I always wondering how to write it correctly. It's trombones. Trombones, something also known now as GT gravity, and basically there are systems that lives on a hyperbolic surface. Well, the simplest one that we can imagine, so it's just a hyperboloid. But the hyperboloid is not infinite. We just put some cut here, so there is some function that describes this cutting, and also the system looks very simple. Well, it's still infinite dimensional due to the presence of this function.
Actually, what you have below? It's geodesic or?
Geodesic, but to be honest, I only in the very last part I will tell about something that is below. So for the most part, we just don't care about what's going on beside this geodesic boundary. But it's geodesic, so this one is geodesic boundary with some fixed perimeter P, and we want to, or whatever, so it was due to probably many people like Stanford, Wheaton, and many more, so that was some hot topic in mathematical physics. Make some description of this system. What I mean under the description, some sort of a goal is to find action of, on the physical level of rigor, that in some limit that limit like n to infinity, n will be so I will use so let's say be just sort of degrees of freedom in this system. And the limits produce something that is known as a Q potential. Q potential, let me write it, so it's where S is a Schwarzian derivative. And maybe something else. We'll see what else. So a hypothesis is that we may actually imitate this system by something that we call a cron, so due to Alexander or myself maybe to, or full cron. Namely, let's consider instead of this picture another picture. So it's always happened with this joke, I know. So consider instead the system where we have n what we call the bordered cusps. And just enumerate them. So cusps, so they're infinite, but we put decorations by Hor cycles. And well, that's make all lengths finite. And let's just enumerate them from 1 to n. No, let's make it from 0 to n minus 1 by some stupid reason. And what we know about this? So we know that in hyperbolic geometry we have what is called Fenhill, Nielsen, or Goldman bracket. Goldman bracket, let me use Goldman bracket for lambda lengths. I will say what is it of the geodesic curves that goes from cusp to cusp, like that. So lambda lengths, because we enumerate all of them, so let's just, it's exponential of geodesic, of half geodesic lengths of the corresponding curve. And what we know due to, well, Bill Goldman probably didn't consider this, but it definitely was considered by Bob Penner and other people. So on the set of this lambda lengths, we have very simple relations. So first of all, we have a Goldman relation. Well, let's call it Goldman. Also, it's not probably precisely due to Bill. So if we have two curves like here, with a single intersection, let's so put here some indices I, J, K, and L, and these indices are ordered in some cyclic way. Then we have that for this single intersection, we have that is 1/2. So we just split it in two possible ways. Li Kj minus lambda J JL lambda Ik. And we have a standard Ptolemy relations that I believe is due to Penner. That the product of this is just the sum of the corresponding terms. And there are relations.
Is the reason to put overpass and underpass?
Overpass, and yes, so it will be. It will appear immediately. Yes. So this will be some starting point of the construction. And the first part will be just evaluating the sort of what we call a continuum limit. Of invariant, also known as Fenton-Nielsen symplectic form. But first, we need what we probably may call, let's call it good coordinates. In my understanding, these are coordinates that are decoration independent. So let's just redraw this picture, just looking from the top. So we have these pictures, this inside, we have the perimeter, and we generate all these classes. So what can be a combination that is not, and we have a decoration, so we have this in green. So imagine that we have some cusp, and I want to find something that is independent on this decoration. So what we can do, we just use precisely that we have this cycle between, so we take two. Nonetheless, one will be, again, so one will be lambda, so it's cusp number I0, and 0 I goes from, so they technically they don't have a direction, but I put just in case to distinguish between the indices. So obviously this ratio is independent on decoration. So let's call it xi. Some evaluation will show us that this xi has some closed Poisson algebra, so it's for n minus 1, and we can actually make further combinations. They take psi variable psi1 equal 1 and psi I equal basically just the difference of neighbor. And then these xi variables will have a homogeneous Poisson relation. And so this Poisson algebra is non-degenerate. Non-degenerate for odd n, and has one Casimir or even. Okay, so our first task is to, no, probably I will also show one more thing. So let's come back to this picture. Come back to this picture and let's now ask ourselves, what can be sort of nice coordinates that are decoration independent? So let's just, in hyperbolic geometry, by some reason, some role is played by orthogonal projections. So let's make orthogonal projections of all these cusps to the boundary. So the first one will be mapped to the point that we say is 0, then we have delta 1, delta 2, and so forth, delta n minus 1. So just the points on the circle of perimeter P. So we are actually, our goal is to just rewrite everything in terms of these deltas. And the first goal is what is, say, xi. If we have...
Sorry, deltas are measured from where?
Deltas are from 0 to 2p. Yeah.
Yeah, but I mean, yeah, okay.
So just because it's geodesic, so we just it's a geodesic distance along this geodesic.
But you have delta 0, which is distinguished.
Delta 0, yes, it just
Equals 0.
equals 0. Yeah. Just for simplicity. Of course, nothing depends on it. Maybe it's the only calculation that I will show. Just because I promise it's really on the level of high school geometry.
So you mean the length of the boundary is p?
Yes. Yes. If you have like for amusement, so let's.
But it is not 3.14 and so on. This
What?
p. This p.
Being very
The length of the boundary component is not supposed to be 3.14.
No, it's B. It's a real length. So it's a perimeter. What do you mean?
I see. So it's not number 3.14.
It's P is not pi. So, in hyperbolic geometry, we can make this perimeter actually geodesic running from 0 to infinity with periodicity conditions. So, 1 exponential of delta I E of p. So, and so these 2 points are identified. We have the perpendiculars, also geodesic functions that are quarters of circles, and decorations are here. So because this quantity x does not depend on the decoration, we can take these decorations at our convenience. So, for instance, this ratio that we are about to evaluate is just related to the geodesic length of this interval. Because the other one I made these 2 circles kissing, so the corresponding lambda length is 1. And well, so these circles, they have corresponding radius. So here is our 0, here is our 1, and here is, because this is a copy of this, so here is the radius is EP are 0, so since these two circles are kissing, so easy formula shows that this distance that we have here, this distance, recall that it's also 1, so it's about radiuses, and the corresponding coordinates are the same as on this line, so it's 1 in delta whatever I, and here is C. So the first formula that I claim is true is that AP minus 2 square roots of R1 well, so it just follows from this right angle triangle. Okay, second, second I can actually enlarge this circle.
Maybe you can lift this blackboard up and write them up, because it's hard to see when you...
Okay. I can swap them. Well, this is, as I promised, just exercise in the school geometry. So we have this relation. If I consider the circle that is kissing this circle, then recall that all horocycles are at the same geodetic distance one from another. No, I mean that all points here are the same. So the second relation that I claim is that this radius will be I0 prime. So we have again that I minus 1 is equal to square roots of R0 prime R1, and finally xi itself is the lambda length, so it's actually R0 prime R0 1/2. So 3 formulas, and I will need to express xi in terms of these quantities. Solution is that xi hyperbolic sine of delta I hyperbolic sine okay, so this is the formula that I will need. All the rest is just some exercises.
So is it R1 or Ri in the square root?
I take it R1, but they are auxiliary, so we don't need them, because at the end of the day, the only dependency is on deltas.
Okay.
I think the point was you have on the left delta I, on the right R1.
Yes, R1 it's okay, so call it Ri, I don't care, it's
Okay, good.
but it must be considered. Let it stay R1 anyway.
Is there a geometric meaning for the delta i's?
Easy, so it's just the geodesic length of this interval. So because the perimeter is geodesic, so we just measure the length along it. So technically again, so my goal is to present everything in terms of just points on the circle. Okay, so as I promised, so the first goal is to figure out. So we have this. We have this simple Poisson structure, Poisson relations, and first I need to invert them to get a symplectic form. Because, well, I can easily make it for the case of order. And again, some next exercise. So let's just consider this case of odd n. And from this these Poisson relations, we have the matrix A, which is size n minus 1 equals n minus 1, with all units here, all minus units there. And now we ask ChatGPT what is the inverse of this matrix?
0.
Huh?
Attempt to see ChatGPT answer.
So what is the inverse of this matrix? Who knows?
Itself?
Huh?
Itself?
What?
Itself?
No. Would be too simple. No, okay, I will tell you. So ChatGPT answer us. The inverse of this matrix is given, well, maybe up to sign that, I'm not completely sure, by minus 1a plus j and vice versa. And it must be skew symmetric because original matrix is skew symmetric. So it's minus 1 correspondingly a plus j, well, let's say plus 1, but we just change the sign for I greater than j. So this means that we have a nice symplectic form on logarithmic quantities.
And the diagonal is 0.
Huh?
And the
Of course,
yeah.
diagonal is 0. Sure. So 0, 4. So we have the corresponding symplectic form. We can write only half of it because the other half is obtained by just skew symmetry. And after some manipulations, algebraic manipulations, we just can rewrite it differently. We can say that it's now sum from I from 1 to... so I will also introduce, so n is 2q plus 1. And then here we have a sum from k equal 1 to q, v log, and here we have this xi to k. So it's just the same symplectic form written in slightly differently. Why I did it this way? So now, you know, at some point physicists started to do strange things. So we now say, okay, consider so we have this system of particles on the circle, and I say, assume that psi j can be written as g tj minus g tj minus 1, where g is some function from zero, one, to let's see, so it's 0p. And assume that this function is small. So and tj will be just equidistant points on the unit circle. Well, also we introduce epsilon to be 1 over. And I also assume that this function is as smooth as we need. And one more assumption I will make, that it has positive derivative. So everything is real valued. Then what happened with this? First, what happened with this expression? What happened to this logarithm of psi? Okay. Can be identified with, well, second derivative of this function at t to k divided by the first derivative at the same point.
Can I, sorry, again something. So the index I runs to n minus 1. And then you change to q. But then if you insert q, there's 2q plus 1, which should be n. So then you run to n, and in the other one you run to n minus 1.
Let me maybe I no, that's not you.
So in the first
Well, it's one. So that's right. It's the last one is psi to n. What?
No, if you insert 2q plus 1, right? It's n. So the last psi, it's psi n, but in the upper line you have just to n minus 1. Yeah. So if you insert there q, right, for k.
For k, k runs from 1 to q. The last is k equal q, so 2q plus 1 is n.
Yes. And then the first
what?
line, j just runs to n minus 1.
There are some small subtleties. Maybe I have to remove this, but I'm not sure. Well, so what about this? What about this term? If we have a look at this, then we observe that it's actually this term is a Riemann sum. sum of the function that is g. With sample points at midpoints of intervals, each intervals of length 1 over m at the left. Okay.
Didn't mean the logarithm?
Huh?
The product?
D logarithm of the whole product. So what we obtain? So we
Yeah, okay, but you should write the logarithm then, right? On the left-hand side.
So we have that this actually for this term we have a logarithm, and logarithm of minus 1/2 integral from 0 to t to k. Where is epsilon? There is no epsilon because epsilon was eaten by this integral sum. So epsilon is the length of the interval. Plus O of epsilon square. With a minus. So it's altogether it's minus 1/2. So if we integrate, that's so far I don't know. So if we integrate, we get minus 1/2 logarithm of g prime of t to k. Plus some terms that we don't care about, log prime of 0, so it's constant term that will be killed anyway by the differential. And therefore in the limit as n goes to infinity, we have for the symplectic form expression in terms of this function dt. And it is the integral between 0 and 1 over dt. Plus all the concepts. So, what is this form? This form is known to be generated by what is called Gelfand Fuchs cocycle, and it has nice transformation properties under change of variables, which we need to do because so far we made it for a function g, but we actually we need it for another function because g of t recall was g of f of ti. Ti is this function. So it's hyperbolic sine the transformation properties of this Gelfand-Fuchs symplectic form is actually it's minus 1/2 integral over dt. Therefore, T times the first Schwarzian that appears is the Schwarzian of these two functions, G and F. And again, for this, because it's a combination, so this is a combination of exponential function and actually fractional linear transformation. Fractional linear transformation has zero Schwarzian, and exponential transformation produce constant Schwarzian. So the only contribution of this is just a constant. So it's minus 1/2 in this case. And as the end of the day, for symplectic form, we have we just need to so this symplectic form is also of Gelfand-Fuchs type, so we have just this addition to this form. Okay, so this form appeared long ago in works by Alexeyev, Malkin, and also then later by Alexeyev and Main-Renkin in more recent works, and also the same form was in Stanford and Witten. Stanford-Witten approach to these trumpets. So it's exactly the same form that we have in the continuum limit here. Next, what about, so we can also proceed from this form to the volume form. And here we have a setback, a sort of setback, because if we express, because it's obviously this form is given by just this product. And if we evaluate this product, we obtain that it's given now it's I come back to n since delta I over 2 product from 1 to n minus 1 delta i's are just literal lengths of the corresponding intervals of partition. And we need to observe that if we want to integrate, we immediately get infinity. So if we address the problem, what is the corresponding volume of modular spaces here? We need some regularization or action. And there are different variants of this action. One was proposed by Alexander and Jessan. So if I don't need all that, so the variant of action by Alexander and Jessan was probably to take just the sum of SI of length of these horocycles. It has well, as every proposal has some advantages. Advantages is that this form of action is obviously additive. It's clear. But I propose another way, because I want also to make some action that is decoration independent and as simple as possible. So what is simple? So we have this also lambda length between neighbor horocycles. It's Si plus 1, and lambda length, it's signed, so if horocycles intersect, it's not negative because it's exponential, but it can be lesser than the unit. So my proposal is to take action S given by the product over cycle is lambda I plus 1 is I. And the action it's not completely additive, but it's quite additive if we take the logarithm and put here some constant. Yeah. And our first task is to evaluate this expression in terms of the same quantities, deltas. Yeah.
This logarithm, I guess
But
we
it's
might interpret it really as the boundary length, right? Where you say, take all horocycles of unit length and all the cusps, and then what remains of the boundary, this is just the total boundary length.
Well, it's independent on the choice of horocycles. We can choose them at our will.
Yeah, but what I'm saying is if you choose your horocycles such that they have length 1, then your action is just the boundary
I
length.
don't well, yes, you can take them, but then lambda lengths will be some lambda lengths, right? So lambda lengths are not invariant as well, because if we change horocycle, we change lambda lengths.
Yeah, okay. This is a yes or no?
I don't know. Well, we can take again. So at our will, we can take this S equal to 1. Yes, if we want.
So is it product, not sum?
Is it product? Yes, product of everything.
So this will be a sum of lengths, and therefore,
Lambda lengths are exponentiated, so they will be, they appear as.
Because in the first formula you got sum of the sides.
The first formula where? Yes, but it's not, Alexander, it's not. S is action, sorry. It's so, but first of all, what is this? Can we evaluate it? Of course we can, I just write the answer. So something a little longer than so this is actually given, so this product is a product, I from 1 to n. Let's write it as a ratio of 2. First, there is some constant term depending on the p, and then we have. No, let me do it different. Let me just theorem that it's given by this expression. It's sum I from 1 to n. Logarithm e delta I plus 1 plus delta I minus 1 minus sum 1 to n. Where deltas, remember, deltas are these differences between nearest neighbors. One may spot a very much resemblance between this expression and this expression. In principle, this is finite for any choice of this positive, of this constant. But there is one very special choice, namely, and with which I will stay, k equal 1. Because in this case, this factor completely cancels the factor in the measure. So for k equal 1, we can write that this expression
Could you remind us who's little delta?
Huh?
Could you remind us who's little delta?
Deltas are just differences. Delta I minus delta I or I plus 1 doesn't matter. So, and they're cyclically ordered. So. So this can be written as an integral with some factors, 2n minus 1, some stupid factors like p minus 1, but maybe they are not relevant, that I don't know. Integral over delta 1 plus delta 2 plus delta n minus 1 less or equal p. All deltas are positive. And here we have the product. I from 1 to the minus 1. Delta I. Divided by this total product of I minus 1 to n. And here is exponential delta I plus delta I plus 1 minus 1. So this strange combination. So it's actually it's difference between not nearest neighbors but next to nearest neighbors. And we take all such differences. All n of them. So we can check that this formula is cyclically invariant. So there is no issue with that. Well, And it is not singular. Why? Because we also have the condition that delta I minus 1, delta I plus 1 are ordered. So when we move these 2 points, when we collapse them to 0, this point is oscillate between them, so they produce a factor delta I that actually makes this integral finite. Okay, so it's tempting, for me at least, to call this these numbers the volumes of the corresponding parts of this model space. Examples. Well, and probably I have to stop because I cannot move to some perspectives of this. So examples. Number 1.
Can you lift your blackboard up and write there?
Sure.
Then you will see better.
Yes. For n equal 2, it's easy because there are just 2 points and the difference is between the point and itself, so it's p, because we are going along the cycle. So for n equal 2, we have just a simple integral between 0 and p, and we immediately get that it's p. So it's EP minus 1. We have 2 such terms, so it's squared and it's cancelled with that. Maybe with 1/2, but it's EP minus. Again, something tempting, yes, to say that, of course, it's a generating function for Bernoulli. Okay, but this is trivial. The first non-trivial case is n equals 3. So this is really originally, this original full tones. So, and after some integration, I got that it's 1/4 EP plus 1, just to make a flavor of calculation that appears. 1 minus EP plus 2. So it's dilogarithms. They here appear regularly. But fortunately, they combine into 5-term relation. And at the end of the day, the answer is not extremely terrifying. It's p squared plus. Here is p, yes. You asked me where is p. Here. Divided by 2. But unfortunately, I cannot continue. Already the next n equal 4 part, I just was able to make it to a simple integration, but there is a combination of 6 dilogarithms. No way to make it simpler. At least for myself. Again, we must ask artificial intelligence to help.
That is a sum of dilogarithms still.
Yes. But yes.
If you continue.
No. It's sum, but we still to integrate this sum. We have to. So I can write it.
But this is now a non-trivial result if p is equal to 0, right?
Yeah.
But the other one, not. This blows up. No, this also.
Well,
blows.
okay,
It does not blow up. Okay, yeah.
Actually, when in the limit when p goes to 0, we can move further. We can actually evaluate closed expressions, I think. When p goes to infinity, of course, it's easier, but even these two asymptotic limits, p to 0 and p to infinity, can be evaluated better than the complete answer. Well, sorry. Well, but one last statement that I need, that I promised to make a Schwarzian exact, right? So, theory. So if we do the same, I just skip all calculations, just produce the answer, okay? Because this is important, because this is also related, maybe related to what was in the Liouville part of the story. So if we do the same limit that we did when we evaluated this symplectic form, I just formulate the statement and then I stop. So in the limit when n goes to infinity, again, so we have the same 1 over n we declare to be epsilon. This action transforms into there is a constant term which is irrelevant to my mind. Then there is a term that is divergent now, but this term actually is interesting because plus term of the first of the zero order in epsilon is just integral over. So its total derivative we probably, well, it's not zero, but it's p, so it's just constant. And probably the most interesting is the first order in epsilon. So it's if yes. Or so this actually it's one way of writing a Schwarzian integral of a Schwarzian derivative. So we actually get that this term can be just written, so I can just replace it by the Schwarzian of this function S of f. And this is in perfect agreement with what was obtained by Stanford and Witten, and also Alexeyev and Main Rankin in their last papers. But I also was interested in this term, because this term is what was called anomalous term in Liouville. And if we technically make expansion in epsilon, it's actually a leading term. But to be honest, I don't know. Well, it's probably to other guys to interpret this evaluation. But this term also appears here. Okay, so I have to stop. Definitely. Thank you for your attention. Sorry for.
Are there further questions?
Can you write the formula you mentioned for the 4?
For the 4, yes, I can. Actually, I didn't mention, so we can actually make it for disk. For disk, it's even easier because then we can move up to 6. But we cannot glue disk to anywhere, it's just a disk. Because this cron we can put on the top of something, but for the disk we. But yes, I think for maybe. So it's still we have one integral. Integral between 0 and p, dxi. And here this combination of the logarithms I promised. That's it. Would it be different signs that we can express for instance? But for instance, we have these two terms with reciprocal arguments. Would they come with the same sign? We can rewrite it as some logarithms. Also, the next integration will be nightmarish anyway. But at least we can, but they come with these signs. I checked it several times, and so we cannot probably simplify it further.
So we don't have, unfortunately, any more time for further questions, so please ask Leonid, because it is now the lunchtime, and as Volodya Fogg taught me yesterday, so I wish you bon dégustation.